All right. So we're gonna use we're gonna introduce how to connect to Goliath cluster and how to use it. Goliath cluster is a supercomputing cluster capable of running large simulations. It's made up of multiple supercomputers. The way how it's being organized is that you just need to go to one computer and launch your application, and once your application is being launched, they will give you internally they will assign a specific computer to carry out your simulation, and once it's been done, it will saved at your designated location, so that you can see how the result goes and do a post-day analysis. In general, all the clusters has relatively slow process to do run simulation as compared to your local PC. But the advantage is really that you can run multiple simulations at the same time, and also it has a huge size of memories. So that's basically the advantage. And in general, say some of the simulation might take 50 days, but at the same time you can run 50 simulations, which is impossible for the general PC. So in average, one simulation is 1 day if you put in 50 simulations at the same time. So it actually saves a lot of time. But the the smart part for the user is that you really need to know what you are doing, so that within the 50 days you expect what you're gonna get, rather than some of the result that will require another 50 days to run. So that's the part you need to be aware of. Currently, I'm using a Debian system to connect to the supercomputing cluster. At the same time, you could also always use your own computer to talk with it. So let's say if it's a Windows system, you can use PuTTY. I'll show that quickly within the Windows background. So first of all, we will have a command interface in my computer. That's going to be exactly the same if you use PuTTY. So you need to really know what is your computer located and where is your username. So for my case, I would have this as my username, and the cluster location is Goliath Labs uq.edu.au. So once I click that, names of UQ, Goliath. Yeah, that's a correct name, which is strange. But what does this mean? So let's try Mango. Yes, Mango works. Oh, okay, EAIT, sorry. Okay, there you go. So then it gives a response asking your password. So you just need to put in your password, and you will be able to see the welcome page. Once it comes with the welcome page, you end up with a typical bash system where it tells you where is the address, where is your computer. So that's the command prompt where you communicate to. So it's based on POSIX language, so it's typical bash language. You can use the typical things, say pwd. That tells you where are you. So currently I'm in home staff uq cz and then you use ls to check what is the existing directories and files. So the ones that are showed as blue is the directory where you can cd into. The white ones here are all files, and the blue ones are directory, just said. And these ones here, the blue one is actually executable. So it's the file that you can use / to execute it. So I can run SUTRASET gf2, say this, then you will see it comes with error, and the error is because we execute it and it requires the input for the SUTRASET, but it doesn't find it, but at least you see the program is actually running. So that's the files you had. As we said that this is basically a portal for a supercomputing device. So this is just one out of so many. We can always use PBS nodes to find out how many systems are there. So it's a lot of information. If you really want to know how many processors it has, you've got the MP for every device. So this is a one computer. It comes with 24 threads. If you want to basically see the key thing, you could say grep MP. Then it tells you that this is the number of computers we have it here. So if you do a simple add up, you know how many processes or simulation, one core simulation is able to run at the same time. So that's basically the capacity of the system. The second thing is that the supercomputing devices are always designed for use by so many people, not just by yourself. You need to see, how many people are around you. So you can use a typical command, say who. That tells you who is already in the system, right? And you could also use SQUE commands to tell that how many simulations are currently running. So in the current one here, we would have these numbers, and each line is actually either it's a running simulation or it's a pending simulation, depending on the status given here. The user is who are using it. Status is the current situation. So PD means pending, which is not running. The R here means it's actually running. And so this is the username who is actually running it. And also you would have the queues, the type of queues. So we have very different queues. And why there are different queues? So it all depends on the nature of your simulations. So some of the people want to use 8 cores to do one job in a very short fashion. So in this case, they can design a specific queue, say that this queue is going to be here for only 1 or 2 hours, but they will need 8 cores to run at the same time. Whereas the other queue would be, say, we will only use 1 core, but we want to run it for 50 days. So the system would smartly, so if you know like the nature of your simulation, and also go to your specific description of the cluster, you will be noticed that which queue is for what type of the jobs. So for us, for SUTRASET users, usually we use Macondo queue, and this queue usually will allow you to run for weeks, and you can run multiple simulations at the same time. So this is basically the nature for the Macondo queue. The rest of the queue, you would say GPU and batch, and again, if you need to use different queues, then you need to contact with the administrator to find out which would be the best. But for us, usually Macondo queue is the best for running 1 core long-time simulations. Now, if you think about how you are able to establish a simulation, I have an example here. So here we've got the HPC trial. So I go to that directory. So I use cd HP trial, HPC trial. Then I move to that directory. And to see what is around, you can use ls. So I've got quite a few commands which we run before. So to make it easy, what we could do is that we delete all the output file we did before. So it would be error, output, and out. And out. We delete those files. And I even don't know what hpc.ssh is. Okay, so this is actually a previous batch system. So it's called the batch talk. So it's a different managed software. For talk-based supercomputing management, they normally use PBS to control the multiple computer and then let them work together. In this specific instance, Goliath, we use what we call SLURM, S-L-U-R-M. So if you want to see more details about how to use Goliath, you can search from Google that say Slurm supercomputing and basic commands or tutorial, you can see more details. So in terms of slurry batch system, we can see that the name to specify the configuration is basically hatch spatch rather than PBS, right? So this is the system that we are going to use. So if we look at the the typical running script, you will see it starts with shebang, so it's hash exclamator bin slash bin and bash. So just copy it, don't worry. So it's just the typical pattern. So that tells you that this script is going to be parsed by bash. And the second thing we have here is, so it's the same header, s batch, and double dash nodes 1. So this nodes 1 means that we only use one node to carry out the simulation. So the node here is equivalent to a PC. So if you need 2 PC run one simulation, then you say node is 2. The second is number of CPU cores per task. So it all depends on the type of simulation you can run. So the CPU per task for us currently is 1. So you could specify that by 2 or 3 depending on the type of the simulation. So some of the people were asking, which is the question that I always receive, is that the code is constructed by one core only. If I specify here, say to 2, will my simulation speed up? The answer is clearly no, because this only tells the allocation of the resources designated for your task, but it doesn't tell how much actually being used. So if you specify here as 2 and you still run a simulation which only use one core, basically the second core is not being used. But nevertheless, if the total number of cores you can use is only 3, you're not able to run the second simulation because you've been registered to use 2, but the second one is not being used. So it is always good to know exactly how many cores you will be used during the simulation. But at the same time, you see that some of them say, you know, my program is able to run 8 cores, but to be able to gain more access, can I actually just specify here as 1 so that I can run as many as you can? The answer is again no. The reason is because that once you have the number put in here as 1, the system will check actually how many cores you are using at the same time. If the system is very stringent and find that the actual number of cores being used as 8, whereas the specification here is 1, they will kill your program. And we are not sure whether batch has been doing that, but it's always good to have a better understanding of how many cores you have been used, you will be used for the program before you specify these numbers. So in terms of Sutra users or SUTRASET users, one node, one task, that's the typical thing. Okay, so the number 3 here is the maximum war time. So the war time is 500, so here is actually 500 hours. It's roughly equivalent to 20 days. So this one is that the estimated time to carry out the simulation. And a lot of cases, you don't really know how long does it take to finish your simulation. So in that case, just make this number be generous. And again, if the batch system is being configured in a stringent way, once your simulation time has bypassed the critical assessed time, the program will be killed. But I believe that Goliath is not doing that because it's our cluster and it's user friendly. So in this case, it will not be being terminated. But it's always good to roughly know the simulation time required, because one of the way to configure a batch system is that everyone would have the specific number of CPU hours for you. So you don't want to overuse it. So if it's overused, they wouldn't allow your simulation to run, right? the name of the job here is basically in the system how to tell how to differentiate this job as compared to the rest of the job. Again, batch system is able to run multiple jobs at the same time, so you want to make them different, and the job name is a tag to tell the difference between. And then the one below here got the S batch, so they will tell you mail type. So the all result here, the all value here means that when the simulation is started, ended, or aborted, they will send an email to your specific address. So here, this is the address, right? Then run simulation. So date, this is a right bracket, output, and 2 error. So this is basically a simple simulation. What does it mean is that we all know that date is a command that tells you the current date. So let's say if I can run this, we can consider this as a simulation, and once you run date, they will tell you exactly what is the date right now. You could consider this as a simulation as well. So the command, the example here will say that run the program date, put all the screen output to the file named output, put all the errors you find to ERRO file. So to run this, to put this simulation into the system, what you could do is that you say sbatch aaa.sh. So that's the command to register your simulation into the supercomputing system. So once you run that, they will say the job is being submitted, right? And also they give you an ID. And I believe that this simulation can just run by a snapshot very, very quickly. So if I do ls right now, you will see the result already. So again, cat ERROR, do we see any result? No, there's no result, because a cat is basically display the files, the content in the file without opening any interface. If I look at the cat output, they will tell you the time, because that's basically the outcome for running a command called date, correct? And the final thing is slurm out. So maybe this is a summary of what's been done, so that nothing is there. So that's basically a completion of a simulation. So if you are running different program, then you are able to use the similar way to do it. For all the users, for the Sutra users, you always can download your own Sutra file and then compile it here, and then you are able to run the program. So the way of doing it here is that you first clone from the system. We need to find out SUTRALAB, SUTRASET from GitHub. So usually you need to copy the address for SUTRASET, and then you basically say, so currently it doesn't have anything else. Then we can use git clone this. So that will give you unable to access. That's strange. Oh, there you go. We don't know what happened, but you know, the last clone is not successful. So basically the SUTRASET package is already here. So you can cd into, then you got binary files, example files, and source code files. And you could go to the source code. It comes with a bunch of F files. You could do first make all, which is to compile, and this is Fortran code, so we use gfortran to compile everything. And once that's been compiled, you end up with a executable file called SUTRASET.gf, which wasn't there at the very beginning. The file was this, but after compile successfully, you end up with SUTRASET.gf, right? So basically, again, the way of compiling it is to go to SUTRASET src, use command make, and then use another command, say make all, to be able to get our executable file. So that's basically the way. Now, we can run this program. We can run by two ways. First is to go to where your file is located. So we can simply run an example, say cd SUTRASET, and then examples. So we could run, let's say, Fujimaki, which is a well-established simulation file, simulation configuration. So this file here, you see it doesn't come up with any executional files at all. So you have the ICS required by Sutra, INP required by Sutra. ET-INP here is the input for evaporation. We also have the lab results, the result from the laboratory, and also the Sutra file. So we want to run it. We typically have two ways of running it. The first way is to refer to the Sutra GF in here, and run directly from the command line. This is doable, but it's not preferred in a way that the program, if this window here, this window here somehow terminated because of my computer out of power, the simulation will be terminated. The second thing is that if you directly run this command in a way, I can show you how you can do that. So you tell this address here, and then just refer to SUTRASET GF, right? And then you are able to run the program like this, right? So this simulation run is not being registered by the supercomputing system, because you're basically using the reception, the portal, to carry out your simulation. And then the problem is that once I switch off this window here, this program here is going to be terminated, which might not be the case that you want. The second way, as we normally suggest, is to use the supercomputing system. So in that case, what you're gonna do is that I just terminate it. So to show how everything runs, then I can delete one of the output file. Let's delete two of the output files, right? We need to copy the AAA SH and slightly configure it in a way to run the simulations. So what we can do is CP in here to AAASH. We also need to put a slash to where? To the current folder, which is specified by a dot here. So after running this, we basically copy AAASH in this directory to the current directory, which is here, right? And nothing comes up. Nothing come up means that you actually run the program successfully. And now if you use ls, you're able to see the AAASH is here. But the current problem is that AAASH does not actually run the Sutra program because it comes with a date only. What we need to run is basically this command here. So then we need to change it slightly by putting the whole command home stuff uqc2, and then later on this to run the Sutra, to run the program. So the way of doing it is to go to here, change the very last command, right? Sometimes we use wave to tell where is the home address. We don't know whether it's successful because it means that the system actually know where the home address is. We can give it a go, and if it's not the case, you actually need to put home stuff uq this as your home address, because it's never guaranteed that the cloud system is able to know where is your home address. So this is the most secure way to specify where your running program is located. Not actually use waves, because sometimes the wave is not recognized by the batch system. They don't know who are you, right? So let's do this first. And to To run it, again, s batch aaa.sh. When you do that, they will tell you that the batch job is being submitted. So it's 254834. So we can say SQUEUE. So this time we don't want to see all of them. We just want to see our project. Then you can say grep UQ username. You find only yours. So what it tells you is that this is the number, this is the queue we're running, and the name of it, which is test123, and that's my user, and the current status is R, which means it's running. And then the 19 here is like how long has been running. So this is 40 seconds. And for this small program here, we only need to run a few, let's say maximum 2 minutes, and then later on it will change to another status. So at the same time, what we can do is now let's move to how to post the processing the program. Now to post the processing the program, you need to have download another library called SUTRALAB. So SUTRALAB is a post and pre-processing libraries we generated and maintained to process the result from Sutra. As you can see that Sutra basically ends up with a bunch of txt file, and you need to visualize it. So to visualize it, it means that even a size of gigabytes data is able to easily display just by a JPG file. So by looking at one JPG file, you can see the whole story, which is the interesting part of it. I believe the current program is already completed, so it's still running. But at the same time, we can do the MATLAB part. So we can put a large file, and we can still use this to see, okay, so now it's completed. And once I run this program here, once I run SQ, it doesn't come up with anything. Then if you use LS, you will see that the previous file that I have deleted is coming up again, which means your simulation is successful. And you could use a quick way to check the result. So sometimes the SMY files is quite large. You see, it's 149 megabytes. You don't want to open up all, so what you can do, you can use tail, which is only look at the very last few lines of the command. That tells you that the simulation ended, which means the simulation is successful. You could also use V to open it up, but it takes a lot of time, right? So, you know, this is a good way to basically just have a peek of the file rather than open up the huge thing. And if you go to the very last line, it tells you simulation is completed, right? And so that means the simulation is very successful, which is good. Then if we look at the simulation result, the majority of the result is located into the NOD file, ELE file. But once you look at it, it's very difficult to understand it, right? So how can we just use this to understand what really is happening, right? So the best way is to visualize it. This completely makes sense. Just think about the recently how black hole is visualized. So the data comes with petabytes. So I heard the weight of all the disk is roughly a few tons. But you know, the scientist is smart enough to just use one JPG image to display the most important part of it and then stitch it all together. So that small JPG file is able to display all the information within petabytes data, and that's exactly what scientists needs to do. So we need to do something similar. So what we are doing here is basically using supercomputing system. So again, we need to go to HP trial here, and then we need to clone SUTRALAB. So again, we need to go here and then find out SUTRALAB, and then open up here and find out the base address, which is here, right? You copy it. Oop. and then you paste it in here. So say git clone insert. Oh, same problem. Let's do it again. Let's do it again. Why don't they ask me to git clone? Please. No. They don't like it. The remote and hung up unexpectedly. What we could do is try to use another machine. Let's say here, Mango. Okay, let's just do it from my computer here. So cd git clone. So again, here the clone is done in my computer rather than the supercomputer. I don't know why the connection is slightly weak, but nevertheless we can use SCP to copy the whole thing to the supercomputer. So if now after running this, I end up with SUTRALAB directory. So what we can do here is that we SCP the whole directory recursively to Goliath labs EIT.uq.edu.au. You need to tell exactly which address you are going to go. So in our case would be in here, right? Again, we use absolute address. I just use the 2 slashes here. So basically the way we make it successful is to run the whole thing in my local computer, which has a better internet connection, and then copy it to the supercomputing device. So now if we switch off my local computer command prompt, close that window, and look here, you will see the full SUTRALAB available. Okay, anyway, we solved the problem. Now, we need to run this command. So we prefer to do all the post-analysis in the supercomputer rather than in your local computer. There are a few reasons. If you look at how many size, how big is the system, you will see that the Macondo locations, Macondo, has got, so its storage Macondo has got 64 terabytes, and 21 terabytes has been used for the last 3 years, and we still have that much available. And the second advantage here is that this storage has been set up in a RAID system, which means that a couple of hard disks has exactly the same thing. So if you try to access some of the files, it would be much faster as compared to your local PC. So if you want to run all the MATLAB program in your local computer, you actually have to copy and paste from that remote computer into your local computer and do the post-processing. And one of the simulation file may be in gigabytes, so it would take a bit of time, and over time your local drive gets stuffed. So it seems that using supercomputing and system to run the post-analysis is a good idea. The second thing you can see is that this computer here has got 126 gigabytes of memory for you to use, which is usually much larger as compared to your local computer. But then the problem is that if you use supercomputer, it doesn't really give you a graphic user interface. So if you use MATLAB, when you use plot, it doesn't come up with a figure jumped out. So you actually have to save the files into your local disk, and also only copy that file into your desktop and visualize it. So that's basically a trade-off. But if you get used to it, you will find there is almost no difference, and also transfer a JPG file would be just a very short period of time. So we suggest everyone to use this way. But if you have trouble, you can start with remote processing, and once you get fed up with the large number of files transferred between the local computer and the remote computer, you will start off using this way anyway, but you will have a smooth transition anyway. So now we need to run MATLAB in here. So what I would like to do is run the MATLAB by no desktop and no splash. What does it mean here is that no desktop means it doesn't come up with the Java interface. It only gives you the command prompt. The no splash here means that it wouldn't give you a small picture saying that MATLAB is loading. So it's like the bare minimum MATLAB interface. So then you will be able to see something like this. So MATLAB is already here. And MATLAB is following POSIX protocol, which means you can still use PWD, you can still use LS, right? And to be able to see all the files, you can use who. So who actually tells you what are the variables has already been declared. So you could always use clear to clear it out, and then you could say c is equal to 5 and then find out all the variables are. If you so basically this is the bare minimum MATLAB, and so to be able to use MATLAB, a SUTRASET particularly, we need to let the current MATLAB know that you actually have SUTRALAB commands. So the way of doing it is you use run and find out where your SUTRALAB location is. So this is being done by HPC, because we know where it is. SUTRALAB, right? And then you've got M files. And after the M files, you would have SL set path, right? So this is literally the command for MATLAB to know where the SUTRALAB library is located. So when you run this, they will tell you currently this is being loaded. After that, you can see you have the IMP object. So IMP object is a typical command within SUTRALAB, and you can use that command. Now, so as long as we got to the library, we are able to post processing the result we got previously in the SUTRALAB simulation. So we need to navigate to that file first. So where are we now? So we are in SUTRALAB right now. So we need to go to the simulation file that is located in SUTRALAB and examples. No? Okay. Another one. CD example. And we can go to hold on. We are going to SUTRASET. SUTRASET. Yeah. And then go to examples, Fujimaki and Masalomi. Oh, that's where we are, right? Now, how to run everything here? If you are here, I usually will open up two commands, two interface, so that you can see. Let's run it first, and then I can explain what really happens around. So we could do read and analysis this file. So to run it, we can just simply click this. So everything is going, and then later on they have one command that is not running, and the reason it's not running is because that the window is not actually in the docked condition, because currently we don't really have a graphic user interface, so they can't dock the program. What we could potentially do is that we just try to hash that specific line. So what it tells is actually in what command here. So let's go there again. And we bring there, and then I believe it's actually in SL analysis. Then which line has been set? There is an error. Line 39, right? So we can use that to tell this is the 39. That's exactly where the file is located. Let's just hatch this and run it again. SL analysis to see whether it's successful. That seems to be running, which is good. And what does this program here tell is that at the very beginning we ran a program called read at ANA. And what does this program do is that they have two files to run. One is SL read and then SL analysis. Read is basically to read this file into the system. And the ANA here is to do the analysis, which is literally visualize the whole thing. So currently they are still running, and the running is basically try to visualize all the simulation result using a video. So I hope that after the program running successfully, they will give you an AVI file so that you can use the AVI file to see what is going on. So you've actually got another new file processing, and you could later on access this file later. So we have a couple of ways to access this file. Okay, so it's finished, so that means the program is completed. So we need to visualize that. And again, the supercomputer doesn't give you a interface, so you need to copy it to your local computer. There are a couple of ways that you can do. I give you a few ways you can do. First would be using SCP. Let's say currently would be UQ Goliath Labs EAIT uq.eu.au, and then you copy the whole thing and Linux AVI here, and then paste it. So by doing this, they didn't find out the directory. I think the reason is because they don't understand the waves. Oops. Oh, okay. So Sutra, hold on. So we need to do this again, SCP. So instead of going to a relative address, let's just go to the absolute address, which is here. and then linux.avi, and the location is here. So remember, I run this command from my own computer and copy the file from the remote computer into my computer, and once I run that, they are running. Okay. Now, how can you visualize it? You use a command called Linux VLC, which is the typical VLC. You are able to see the results. So basically, by doing this, what do you find? So, well, let's quickly show what it's doing here. So this simulation here has got a small column, and the bottom of the column is connected to water reservoir, and above you have the evaporation taking place. And because the reservoir has got the saline water, this process will accumulate the salt. So if you look at the salt at the very beginning, it's relatively small. It's almost like homogeneous within the column, but later on it increases at the surface, but underneath doesn't affect it. And because of the salt accumulation, you have two things happening. First is that the salt thickness increases on the depth, on the surface. At the second is that because of the salt thickness increases, the evaporation decreases as well. So if you look at the evaporation whole process, you have almost like two sections of decrease. The first decrease is when there is no solid salt, almost no solid salt, but the solute increases. So the solute actually increases the osmotic potential, and that causes the evaporation decrease. The second part is that when you reach solubility limit, the concentration almost never increase, but the thickness increase drastically, and that increase further decrease the evaporation rate. And also we have the laboratory experiment result, which is the evaporation rate, the flow, and also the saturation profile. So that's how it's being run. And then you can see here the result is being successfully visualized, and we visualize it from local rather than remote. So if you have a Windows computer, what you could do on this is that you go to the Windows and then find out your WinSCP. Yeah, so that's the command. And in here, you need to have Goliath labs EAIT uq.edu.au, and username still the same, and we can save it. And after saving it, you log it in and just click yes. Really? Oh, it doesn't like me. Okay, so it's successful. Now, if you look at this window here, you've got your local computer, which is here in this section, and another one is remote computer. Remember, we have the HPC trial, right? We also have the SUTRASET, sorry, and then examples, and then the Fujimaki example, Masalomi. So you see the Linux file here located, right? So see, currently the file, the maximum is 152, but as the number of cell and simulation time increase, the whole folder could easily increase up to like gigabytes or even terabytes. So in this case, you could always just analyze the simulation from MATLAB remotely, and then only output the visualization file to another system, to another computer, and then you can just run the visualization to see how the result goes. You could also do it interactively. Say, I can show you the other way. You can just run a quick command and then be able to visualize it. Can we open it up? Oh, there you go. So again, we see that using a Linux system, right? And if you want to use the Linux system to run the command interface, you need to use PuTTY. And PuTTY, we've got Goliath labs EAIT uq.edu.au and Goliath. So let's just save this and then open it, and you will have, so this is equivalent to the command line we had before. So that's the same when you access from the Windows computer. So I just quickly do another interactive session to do a MATLAB program. And the way we're gonna do it is that you say A is equal to 1, say 0.1. So what I'm trying to do is that I want to plot a value, say define A as 0 to 10 with a lot of decimal points, and then plot sine A and cosine A basically, and then plot them into a figure, and then see it remotely. Not see it remotely. Save the files into a JPG, and then basically export the JPG into your local computer and visualize it. So I've already defined A. Well, unfortunately, I didn't put a semicolon, so it has a lot of results. Let's say B is equal to sine A, right? Then we've already got that. And then if we use who, then that's literally everything. Oh, we've got quite a lot of things. Let's just clear it up. Then it doesn't have that. So let's say A is that, B is sine A, okay? Then what we can do is figure. And nothing comes up. Again, it doesn't have user interface, but it's there anyway. So you could say plot A, B, right? And then you basically want to save the figure. Let's say now it's already been plotted. And then you could even say X label A, Y label B, right? And then we need to save the figure. The way of saving it is actually a FEIG file. So normally, well, I don't remember that, but I think it's good to have an interactive session. So you go to Google and find out, say, MATLAB save figure as FIG, right? And then you find out the specific commands. So that's here, right? And then you just literally paste it in here. So it's called the peak file.fig file. And once we go to the online, the WinSCP system, they will tell you that you will get another new file by refreshing it from here. There you go, right? And you can copy and paste in here, and then you can visualize it. Now, FIG file can only visualize if you have MATLAB there, but I don't have a MATLAB, so we need to save it as a JPG, right? And to do that, we need to find out the command that is able to save it as JPG file. Say save figure as JPG, high resolution, and then you go in there. So that's one of the commands. And then you basically copy and paste it to your home computer, to your own command interface, like this. So what this one does is that the current graphic holder, save it as full.jpg, PNG, and the type of the file is PNG file, resolution is 300, right? And once you run it, you'll be able to see in here you will be able to see a full.jpg. So I just refresh it again, full.png, and you save it here. And then you'll be able to look at it by double clicking. So that's actually a JPG file. So we need to see, that's basically the sine files, right? So that's literally way how you remotely run MATLAB, visualize the result, and just look at the result, rather than carry out all the simulation file to your local computer and save it. And also we covered a bit on how you're going to run the simulations, particular SUTRALAB, and using run SUTRASET and then use SUTRALAB to visualize the result. So that's all about it today.